What I'm going to present today to you is some provocative talk on some new trends of the field of analog models of gravity based on condensed matter systems, and in particular, ultra-cold atomic fluids. So the organizers asked me to present something which is more provocative. So I chose a topic which is presently in the course of being finalized together with Giulio, who is here in this picture. He got married a couple of days ago, so he cannot be with us. But it's work still in part in progress, so I would be very happy to receive any kind of comment, suggestion, objection, remark from the audience. So please feel free to interrupt me anytime and ask questions. Just unmute yourself in a loud way. Good. So for the ones who are not very familiar with the idea of analog black holes, I don't know what happened. So the basic idea is to create a system of a condensed matter system where some excitations behave kinematically in the same way as a quantum field behaves in a neighborhood of the horizon of a black hole. Here it's a cartoon taken from Wolf website for a fishic black hole. So think of being a fish who's swimming in a river. So in this region, the river flows slowly, so the fish can swim both downhill and uphill. In this region, the river is flowing so fast that the fish cannot escape from this region. They are not able to swim fast enough to go uphill, and so they are dragged into the waterfall. So the point where the speed of swim of fish equals the speed of flow is a sort of point of no return, is an event horizon. So it's a fishic horizon. So if you replace this fish with some generic excitation on a river, you can think that this point will behave as an horizon for this excitation. And one knows from high energy physics and quantum field theory on curved spacetimes that whenever there is a horizon, one expects some Hawking emission at a temperature which is determined by the surface gravity of the spacetime at the point, at the horizon. For astrophysical black holes, one has this Hawking temperature, which gives a fraction of microkelvin for solar mass black holes, which is something which is extremely low as compared to the cosmic microwave background. So something very hard to be observed in astrophysics. On the other hand, in the analog model context, there is the analog Hawking emission of sound, which is foreseen at this temperature, it's written here, which turns out to be in the nanokelvin range, which is to be compared with the temperature of actual ultra-cold atomic clouds, which can be in the same nanokelvin range. So there is something which is hopeful to experimentally investigate, because it's not completely crazy temperature range. There is one more point which makes condensed matter analogs interesting for this analog Hawking adventure, which is the fact that Hawking radiation is composed by two particles. One falls into the horizon and one emerges from the horizon. So the one that we normally consider as Hawking radiation is the part which emerges from the black hole. This for the very trivial reason that it's difficult to enter into a black hole and tell to our colleagues outside what you are observing. So, but this is not a peculiarity of, it is a peculiarity only of high energy black holes. In condensed matter analogs, there is no problem in exploring also what happens inside the horizon. So Hawking radiation can be observed in an easier way just by looking at the correlation between the two particles, which are created simultaneously by the Hawking process. Hawking emission consists of the two particles, so one looks for the correlation between these two particles. And this gives a much stronger signal as compared to the trivial thermality of the Hawking emission. And this is a key advantage, which was exploited in the recent experiments carried out in the group of Jeff Steinhauer in Haifa, where it was this Hawking radiation, analog radiation, was observed indeed by looking at this correlation signal. This was our old theoretical predictions that we carried out together with Roberto, Sandro, Alessio, and Serena many years ago, 2008. And here it was the experimental observation by the group of Jeff Steinhauer, where this mustache that we nicknamed Balbinot-Fabry mustache has been experimentally observed in this plot of the correlation between density fluctuations on either side of the horizon. So this first holy grail of analog models has been found, as Harrison Ford did here. So what is the next holy grail for this field of analog models? So one very widespread concept in these quantum field theories on curved space-time is the so-called backreaction. So the backreaction is the coupling of the quantum field which lives on top of a space-time with the underlying space-time. Make the simplest example. Take a black hole, let it evaporate under the effect of Hawking radiation. If you stick at the level of the quantum field theory on a curved space-time, the emission will persist forever. In reality, however, the black hole is losing mass via this Hawking radiation phenomenon. So eventually it will evaporate away. So the big question is, what remains there once the black hole has completely evaporated? Is there any trace of what had fallen into the black hole in its early times, or all information has been dissipated and disappeared? So this is a very important problem on information theory called the information paradox of black holes, for which has been a huge literature on which I don't understand much and I will not enter. On another perspective, there is the importance of this backreaction of the quantum field, which is emitted by Hawking or even superradiant phenomena, is related to what basic physics can be learned from the black hole instabilities. For instance, the instabilities due to black hole superradiance, as it is here summarized in an excellent way in this talk by Paolo Pani, my colleague from Rome. So here again, there is a lot of literature investigating how the backreaction of the quantum fields which are emitted by these black hole instabilities can stabilize the evolution of the black hole, creating the so-called black hole hairs. And another big question for the gravitational wave community is how this backreaction effect can be observed from the gravitational wave emission from these astrophysical objects. So this here is to give you a framework, a flavor, that this problem of backreaction is really a very widespread problem in modern astrophysics, cosmology, particle physics, and even information science. So it's very interesting to try to see what analog models can explain of these physics. Of course, we are very well aware that analog models are excellent in simulating quantum field theories on curved space-times, but they have problems in simulating that part of equations which deals with the Einstein equations of relativity. So how the curvature of the space-time is related to the stress energy tensor of matter. So this part is not implemented in the analog models. Still, in spite of this problem, we are wondering if there can be some interesting physics being visible in the higher order couplings of quantum fluctuations to the underlying macroscopic flow of the Bose-Einstein condensate. Or from my own quantum optician's point of view, can my quantum optics concept teach anything interesting on these black hole physics? Can they be toy models of black hole physics in some sense? So this is the big picture on which I organized this talk, following the recent accomplishments of the research of Giulio Butelli. So the simplest toy model is a single mode cavity in which I consider the dynamical Casimir emission. So many of you have seen this cartoon from my Padova colleagues Pino and Uoso about the dynamical Casimir effect. So dynamical Casimir effect is basically take a metallic mirror cavity, shake the mirror fast enough. This motion of the mirror will create some 0-point radiation in the cavity. So when you open the cavity, you will feel some radiation coming out from the cavity because of dynamical Casimir emission. Of course, this radiation is very, very weak. So this cartoon character does not suffer any risk of being burnt by dynamical Casimir emission. Anyway, the main idea of dynamical Casimir, you have these two mirrors. You make them oscillate. These mirrors are metallic, completely neutral. Still, they emit electromagnetic waves by converting 0-point radiation into observable radiation. So this is a process which emits radiation. So you can expect that the energy for the radiation will come at the price of the mechanical motion of the mirrors. So when I mechanically move the mirrors, I will feel some friction force, some 0-point friction from the vacuum. This is a kind of cute and intriguing effect. Whenever the vacuum converts 0-point fluctuations into real radiation, the moving object will feel some mechanical friction. One of the first calculations of these phenomena were reported in this old paper, where gave some estimate of dissipated energy, and if you plug in numbers, you find the result, which is ridiculously small. So no way of observing this effect with macroscopic objects. So here comes quantum optics into help. The first attempt in finding a quantum optical configuration mimicking this friction force or dynamical Casimir effect is this all-optical setup, which is basically based on a 3-level atom, which can be brought from the ground state to a pair of excited ENF states, and only the ENF states are coupled to a cavity. So whenever the atom is in G, it's basically non-existent for the cavity. When the atom is in these two states, it resonantly interacts with the cavity mode. So in a way, the cavity sees a moving environment when the atom is repeatedly brought from the G to the E state and vice versa. This can be done by driving Rabi oscillations between these two states. In this way, you put the atom in and out from the cavity back and forth, which is equivalent to periodically shaking the mirrors of the cavity. So one expects that some dynamical Casimir emission will take place. Here is plotted. And corresponding to these peaks of the dynamical Casimir emission, one finds an absorption of the light on this blue transition. So the fact of that the atom emits dynamical Casimir radiation in the cavity has an effect, a back reaction on the laser field, which is modulating, which is creating these Rabi oscillations of the atom. So just by looking at some quantum optical observable here, one finds peaks due to the dynamical Casimir effect, which is a sort of friction created by the dynamical Casimir effect on the atomic dynamics. Very good. So this is a cute experiment, seems reasonable, but it's technically very hard to be done in practice. So we tried together with Giulio to find some simpler configuration. And our colleagues from Sicily basically spoiled our idea because they were faster than us with this great PRX paper, which proposed this very simple setup. It's an optomechanical cavity where the cavity is attached, is mounted on a spring, so that one of the two mirrors is attached to the spring. So it does not move freely as it happens if you are just moving the mirror from the outset. No, now one mirror is fixed, the second one can oscillate freely. So in this way, one can let this spring oscillate, and if the spring is tuned to the right frequency, this motion will create pairs of particles in the cavity by dynamical Casimir effect, which then will result in some emitted radiation. At the same time, this emission of dynamical Casimir emission will create some friction force on this mirror. So how to implement this device? Of course, having a spring which resonates at a frequency which is achievable, which is accessible to optical techniques is an extremely difficult task. One can work in the gigahertz regime, but it's really borderline for acoustics. So we looked back at the first experimental observation of a dynamical Casimir effect using a superconducting circuit. So basically, this experiment was done in the Per-Delsing group and was based on a waveguide. Here is a waveguide plotted here as a circuit equivalent, capacitors and inductances, closed at the end on a squid. A squid device is a superconducting device which is pierced by an external magnetic field, B of t, which modulates the effective impedance of the last element. And as a result, it basically moves the physical position of this final mirror, which is closing the waveguide. So in this way, by modulating the field B of t, one is obtaining a waveguide which is effectively of varying length. In this way, this group was able to report the first experimental observation of dynamical Casimir effect. This object was moved by this externally applied magnetic field, and dynamical Casimir emission was emitted along the waveguide. Very good. So you see that this device is very promising in view of realization of the spring plus cavity model. Just the trick is to consider the B field, which is concatenated with this squid, not as an external field, but like a field which is generated by an external LC circuit. So this LC circuit plays the role of the spring on which the mirror is mounted. Time dependence of this field modulates this squid, so it modulates the effective position of the final mirror of the waveguide. In this way,
Iacopo?
Yes, please.
Hi, it's Ted.
Hi, Ted.
Could you just clarify something elementary here? How is this not just an antenna that's radiating down the waveguide? Why is there no classical radiation?
Because the frequency is different. So this B field oscillates at a frequency which is twice as large as the one which is observed. So here I don't remember by heart. I think this guy was oscillating around 1 giga, and they observed the emission at half the frequency.
Mm-hmm.
It's about 1.5 giga, and here the emission is around 750 mega.
Okay, thank you.
Yeah. So this B field. So here we have the idea is to have another small circuit which oscillates at frequency, say 1.5 giga, and you look at the emission here at half the frequency. So, but you see that the main difference is that the B field here is not generated directly by some macroscopic object, but is generated by a LC circuit, which is a harmonic oscillator, which is coupled to the waveguide. Like here, having a harmonic oscillator, which is coupled to this mirror, which is then coupled to the dynamical Casimir emission. So, Giulio solved the model in full detail, calculating as a function of the frequency the way that this additional LC circuit responds. And here he found that the response of the bare oscillator would be this narrow Lorentzian. When coupled to the waveguide, he finds something which is much broader. Here, for a very strong coupling of the LC to the waveguide, one can see even a splitting into 2 peaks instead of 1, which is a sort of strong dynamical Casimir-induced coupling. So this seems to be a realistic setup, and our colleagues here in Trento were very interested in the idea and are trying to design the optimal setup and try the experiment. So hopefully something interesting will come out in the coming years. So, but what I presented in this slide is the response of this LC circuit to some external drive, where the resonances get larger because of this friction force. But one can also look at the free evolution of the LC after an initial kick. Here you see how the evolution of the LC changes from the green line to the black line because of this dynamical Casimir emission, which makes the friction to be stronger than the bare friction of this LC circuit. Here, the effect is even stronger. For strong DC coupling, one can even have a periodic exchange of energy between the harmonic oscillator, the LC circuit, and the waveguide. So you see there are these oscillations, and here these oscillations are in counterphase. So there is a periodic exchange of energy between the oscillating mirror, the dynamical Casimir, and then back to the mirror. So you have a periodic exchange between mechanical and electromagnetic energy. Quite cute. One feature that Giulio found, quite unexpectedly, is that the quantum fluctuations can be very important in this process. In particular, if the spring or the LC is not exactly on resonance with the waveguide resonance, there can be a very strong quantum fluctuation effect on the motion of the mirror. So the mirror oscillates, but receives by the dynamical Casimir emission a fluctuating force in time, which not only breaks its motion, but also makes the motion to decohere with time. So the phase of this mirror oscillation will quickly dephase in time. So will become a random phase. As you can see in this plot, where for different times from the beginning, one starts from a coherent state. At late time, the phase of this B field, which is the harmonic oscillator, has completely decohered and is become a completely random phase. Which shows the kind of unexpected effects for us that the quantum fluctuations of the dynamical Casimir emission can have a very important role in determining the dynamics of the oscillator which it suffers this damping force. So after understanding the single mode cavity, we ramped up to a more complicated model based on an elongated BC. So inspired to early works on back reactions in black holes in atomic BCs, we tried to look how these quantum fluctuations can affect the motion of a BC. In particular, the early literature uses the analog of this Einstein equation, where you see that the curvature tensors are coupled to the average value of the stress energy tensor due to the quantum fluctuations in the quantum field. So in our language, if the Hawking radiation or the dynamical Casimir radiation take place in some field, it's the average value of the stress energy tensor of this field, which back react onto the curvature tensor of our spacetime. This is the typical formula that you read in books, and it's the so-called mean field description of back reaction. What I will try to present to you now is some investigation trying to include all fluctuations of these emission back onto the effective space-time. In order to do this, we consider a simplified geometry that people in cosmology will recognize as a sort of preheating stage of the universe evolution. That is, at the end of the inflation, when the inflation parameter has reached the minimum of its potential landscape, it performs some oscillations around the minimum, and these oscillations will decay by emitting pairs of particles into the universe. In the case of our BC, what we do, we use a breathing mode of the BC as the initial oscillation. So a breathing mode is a cylindrically symmetric oscillation of an elongated BC, like my hands, which decays into pairs of dipole modes, which are oscillations of the condensate, which move in space along the transverse direction in the trap. So if you're not too familiar with BC modes, you have just to think that this BC contains several branches of particles with different masses. In particular, we consider an excitation at kz equals 0 in the breathing mode, and this decays to half its frequency as a pair of excitations in the dipole mode at this frequency, around mode 32, 35. So our numerical simulations are done by the usual truncated Wigner approximation for the dynamics, which is somehow a GPE with stochastic initial conditions. We solve it numerically by brute force, and we obtain some kind of clear experimental results of our numerical experiment. So at this time, around t equals 30, we create a strong excitation of the breathing mode, which is this the dotted line, which is excited only on its first component, because we excite the breathing mode only at kz equals 0. Then we let the system evolve, and you see that this excitation in the breathing mode indeed give rise to some excitations in the dipole mode, around mode 32, 35, which exactly is the frequency that one would expect from the energy conservation condition.
There's 1 minute left.
Okay, good. What I'm at good part. So you see this emission in this part. What is very interesting is that if you look carefully at the intensity of the dipole mode, this grows in time, but the breathing mode starts decaying for energy conservation, because this energy which has gone into the dipole mode has to be taken out from the breathing mode, which suffers some back reaction in the form of friction. But this is not the only effect that the breathing mode feels. Also, you see here the unexpected effect that the breathing mode is no longer the excitation peaked at a single mode, but gets broader. It gets broadened in the sense that excitations in the breathing mode expand over a wide sequence of modes. This means that the back reaction of the emission to the dipole not only damps the excitation of the breathing mode, but also introduces some fluctuations into it. In particular, you can see from this picture that at 0 time, the excitation of the breathing mode is coherent in the whole cloud. At later time, it remains correlated only at short distances. It's like an oscillation which is coherent everywhere. It becomes completely random because of this friction force. And this is completely different from what one expects from the standard picture of backreaction, where what enters into the Einstein equation is the average value of the emitted field and not quantum fluctuations.
Excuse me.
Yes.
We can see in your picture that you also have some Higgs modes, that Galton mode, which are excited during the evolution. Do you have any commentary on this excitation of the Galton mode?
You mean this part here?
Yes, exactly. And
This
at
part...
late time, we can also see it quite clearly.
Okay, though, this initial part is a small excitation, and we are pretty sure it's the consequence of the numerical formalism we are using. But this is a small effect. Here, where the Galton mode becomes very large, that's again an effect of quantum fluctuations. It comes from the fact that quantum fluctuations in the breathing mode and in the dipole mode also react on the Galton mode. And think that the Galton mode is very sensitive to perturbations because it's basically the excitations of the condensate. So any small excitation will perturb a lot the condensate. It's a very soft object. So this is another trace of backreaction. Very good. So I'm ready to conclude. So these are the preliminary numerical data which show a strong evidence of this backreaction effect. But there are many other directions in which this analog model community is moving in this time. Superradiance is one of the hottest topics, and I guess that Silke will speak about this kind of phenomena in one of the next days. Then there are other things which are very Mainz-based, which is this part on two-level emitters, which are dipole coupled to curved space quantum field theories. This is something which is studied a lot by Jamir Marino in Mainz. And here are some interesting long-term consequences of these backreaction effects, which are to try to understand what is the meaning of these quantum fluctuations in high energy physics. So are these quantum fluctuations of backreaction of any importance for instance, on the anisotropies of the universe, or do they have any role in the intrinsic fluctuations of a black hole metric in its stationary state during evaporation? With this, I thank you for your attention. Here are a couple of further reading, in particular, this excellent PhD thesis by Luca Giacomelli, who just graduated. You can find it on the UniTN archive, where you can find a lot of interesting things on superradiance. And as a last point, I cannot but conclude my talk by thanking the person who mostly contributed to the shaping of our analog model community, and who unfortunately one year ago passed away, and I wish to remember him. Thanks a lot.
Thank you very much, Iacopo, for a wonderful and inspiring talk. We have several minutes for questions. Please, yes, please unmute yourself, and yeah, I see. So okay, you can.
I have a question, two questions about the last thing you discussed, Iacopo.
Yes, sir. Please, Ted.
I'm sorry, but I don't actually know what the dipole mode refers to. So that's question one.
Okay, so Ted, think of a trapped BC. This is my hand. Look at my hand. This is the harmonic oscillator. So the dipole mode is when the BC oscillates in the trap. And in our case, we have a very elongated condensate. So you can think the displacement of the condensate from the bottom of the trap at each position being the coordinate of the dipole mode.
So it's a transverse wave in the elongated condensate?
Exactly, the sort of condensate which moves in this way.
Okay, good. And the other thing is, what would be the radius of that cylindrical condensate in your simulation compared to, let's say, the healing length?
The radius, I think, is comparable. It's comparable. I don't remember by heart. I have to look back at the data, but we were in a regime where I think you can see it more or less here. So you see here, the chemical potential is around here, is where the dispersion tilts. And this is comparable to the frequency of the dipole.
Mm-hmm.
So the two are more or less the same.
Okay. And could I ask one other quick question, then I'll just not stop asking about what you said previously about the waveguide system and the dephasing of the oscillator. Exactly. So does that mean that the quantum state of the oscillator becomes entangled with that of the radiation field down the waveguide or in the other oscillator, or what exactly is happening to the global state?
The global state remains coherent, remains a pure state.
So it must be a result of entanglement. So it's no longer a product state of the oscillator and the rest of the system. Is that what it is?
Exactly. Yes, I would bet it's so, because this starts from a pure state. So the oscillator decays, emits dynamical Casimir emission. So there is entanglement between the oscillator and the emitted radiation. Yes. Yes.
Okay, thank you.
So then, Ted, we have to discuss what this means for black hole information.
Okay.
Or Silke will please ask.
Iacopo. Hi, can you hear me?
Oh, yes, I can hear you. Hi, Silke.
Hi, thanks for your talk. I have a couple of questions for you related to your parametric resonance experiments. Very nice results. So one conceptually, so when we talk about back reaction, it's just maybe to get what you have is it, so you have mode interaction, right? You say you occupy one mode and then it decays into a different branch in a dispersion relation, which will be the one corresponding to a transverse or dipole moment.
Okay, yeah.
But then back action, as I understand it, and this is coming from sort of a mixture of black hole and analog gravity experiments, will be that because of the excitation content, you would change the condensate itself in a sense of, for example, the propagation speed of your waves would change. So because that will be a change in the analog metric. You seem to think of it differently. Do I get that right? You say back action is just once you cannot just assume this nice quantum field theory and curved space-time analogy, you have to include more terms.
No, in the sense, what you are saying would be the holy grail of my study of back reaction. But it's much more difficult technically to consider a flowing condensate with an inhomogeneous flow pattern. So what we decided to do with Giulio was to take something simpler, which is a condensate, which is initially homogeneous, it's just oscillating in the transverse direction. And still this configuration displays some back reaction phenomenon in the sense that the excitation in the quantum field, which is this dipole mode, back reacts on some other field which plays the role of the metric.
So that sort of, it sees an average condensate. It's a condensate plus a dipole mode on it. Is that what you have in mind? That would be
the condensate plus the breathing mode is the metric.
Yeah.
Then the dipole mode is the quantum field theory on top of the metric.
So we did a long time ago, maybe we can discuss it also offline, simulation of parametric resonance. And we also noticed that because the system eventually should go at equipartition of energy. You know, it's like because it becomes classical, you know, all this.
Yeah.
And we didn't notice that. We didn't get that. And then we realized if you work with a modified sound speed then you would get this equipartition of energy. And we found this paper by Drummond, which would indicate that how you would calculate this, you know, you redefine your energy levels. And it seemed to happen some things because you have this strong nonlinearity that you have to redefine your energy levels in the system. And so it was something we could discuss maybe offline. And the last comment I wanted to ask you, when you do these experiments, so we are doing this kind of experiments in classical system, 2 fluid systems. And so one of the problems we have is we always create a little bit, you know, we create half of the frequency, driving frequency, but we also, because of the boundary conditions in our system, we also always have a little bit of creating actually at the driving frequency itself. Do you see something in your data that you always have something which is not something I get from a nonlinearity, but something which
we were somehow safe from this because of symmetry. Because the dipole mode is odd, while the breathing mode is even. So you cannot create an odd mode out of an even mode. So here we are safe. What can happen is that more complicated mode conversion effects do any kind of garbage you can imagine. Then you can have many other couplings which can be very annoying.
Yeah, but it's a nice.
So you see, Silke, in this last picture, when the last time, you see plenty of peaks.
Yeah, you get.
And all these peaks can be attributed. Now I really cannot remember what was what. Is 867, 70, must be this, half of the frequency on the Goldstone mode. Then you have this mode which is 107, which is what? Is exactly what you were saying. Is the Goldstone mode at the same frequency? Is this peak?
And actually, just one last question, then same as Ted said, I will just be quiet. What is your initial state?
I take the Bogolyubov ground state.
So 0 temperature or?
0 temperature. With a caveat that we may have quasi-condensate features, so we have to take them into account. But it's 0 temperature. 0 temperature with the quantum noise, of course.
Yeah.
With the truncated Wigner way of including quantum noise.
And you think in the experiments you're there?
No, I'm not doing experiments. I'm a theorist. So
I thought you also have some experimental.
no, these are numerical experiments.
Okay. I thought you also work with.
Oh no! I would be too much a happy person if I had experiment.
Okay.
We are still in the phase of waiting for the response of our funding agencies.
No, yeah, but I'm sure. So I mean, if you don't, someone will do these experiments, right? Because they're really interesting. It's quite.
It's kind of simpler. For instance, the group at Maryland could do these kind of experiments in the toroidal object.
Yeah. Or also, yeah, obviously Ted is going to talk. Also, I mean, there are so many people interested in this, like now Jörg Schmidmeier, Markus Oberthaler, you know, I mean, there are many people that keen to, I think, look into this in very close eye and study these nonlinearities. I think it's a really fascinating topic.
We had great fun.
No, it's nice. It's great. Thank you.
And this is really thanks to Giulio. He was the driving force of all this.